Imagine a mountain so vast, so powerful, that it breathes fire and smoke. Mount Etna, Europe's most active volcano. For centuries, Etna has been both a source of fertile soil and a reminder of the Earth's inner power. But now, scientists have discovered something remarkable. Etna is slowly sliding towards the sea. The southeastern flank creeps a few centimeters each year, imperceptible day to day, but significant over a lifetime. This isn't caused by dramatic eruptions, but by gravity itself. The mountain's immense weight presses down on a weak, yielding foundation, like a heavy book on a soft cushion. Understanding this process is a major challenge for geologists, requiring deep dives into Etna's history and structure. It's a story told in layers of rock, subtle earth tremors, and satellite measurements. By piecing together this evidence, we begin to understand the restless giant's journey, and what it means for those living in its shadow. Etna's slow movement is a cosmic dance shaped by forces both ancient and ongoing. The question is, what happens next? To understand Etna's movement, we must look back to its origins. Etna was born from the collision of the African and Eurasian tectonic plates, a process that created both magma and instability. The ground beneath Etna is a patchwork of weak, slippery sediments, clay, and soft materials laid down long before the volcano formed. The mountain's immense weight rests on this fragile base, setting the stage for its slow slide. Etna's layered structure, built from alternating lava, ash, and rock, is less stable than a solid mountain. Over time, eruptions have made the mountain asymmetrical, focusing gravity's force on the southeastern flank. The result, a mountain not anchored to the Earth's crust, but one in constant, slow transformation. These powerful forces and inherent weaknesses have conspired to create a living, moving giant. Etna's story is one of relentless change, written in stone and sediment. Scientists once thought Etna's movement was driven mainly by magma pressure, but new research shows gravity is the true, constant force at work. The volcano's massive weight presses down and outwards on its weak base, causing it to spread like honey on a plate. This gravitational spreading happens all the time, not just during eruptions. Magma can act as a trigger, lubricating the sliding surface and speeding up movement, but gravity is always at play. The result, the flank is always in motion, building stress over time. The real danger isn't just eruption, but the potential for the flank to collapse under its own weight. The slow creep is a sign of immense strain, a silent battle between rock and gravity. Even the most solid-seeming mountains are in constant flux. Etna's movement is a powerful reminder of the planet's restless nature. Etna bears a massive scar, the Valle del Bove, a vast depression on its eastern side. This caldera wasn't formed by a single eruption, but by multiple catastrophic flank collapses thousands of years ago. The valley is a stark reminder of the mountain's instability and the power of sudden collapse. Debris fields stretching toward the sea reveal ancient landslides of unimaginable scale. The Valle del Bove sits on the same side of Etna that's sliding today, showing that these weaknesses are long-standing. Today, the valley channels lava away from populated areas, turning past destruction into present safety. By studying the valley's slopes and debris, scientists learn how and why collapses happen. The Valle del Bove is a history book in stone, warning that Etna's instability is fundamental and ongoing. The forces that shape the valley are still at work beneath the surface. For years, scientists tracked Etna's movement on land, but the story didn't end at the coastline. The volcano's base extends beneath the Ionian Sea, hidden from view. To investigate, researchers deployed underwater sensors, GOC, on the seafloor. These devices measured tiny shifts, revealing that the underwater flank was moving too. In 2017, the seafloor shifted 4 centimeters in just 8 days, without any eruption. This proved gravity was pulling the entire flank from summit to sea floor as a single block. The instability isn't just a surface phenomenon, it's deep and far-reaching. This discovery changed our understanding of Etna, showing the whole mountain is on the move. A collapse involving both land and underwater flanks could trigger a massive tsunami. The risks are greater and more complex than once believed. How do people live safely near such a restless giant? The answer: constant vigilance. Italy's INGV scientists monitor Etna around the clock. Seismometers, GPS, satellite radar, gas sensors, and thermal cameras track every tremor, shift, and plume. This data reveals that the flank's movement isn't always steady. It can accelerate after eruptions or earthquakes, Even small triggers like a magma intrusion or a quake can speed up the slide. Detailed monitoring allows scientists to issue timely warnings and assess risks in real time. While we can't stop the mountain from moving, we can watch its every breath, keeping people safe. Knowledge is our best defense against Etna's unpredictable power. What does the future hold for Etna and those living nearby? The southeastern flank is sliding, and while a catastrophic collapse is unlikely soon, the risk is real. The worst-case scenario, a massive landslide into the sea, could trigger a devastating tsunami. More likely, Etna's instability will show in smaller landslides or continued slow creep. Predicting a collapse is difficult. Triggers can be subtle and complex. That's why continuous monitoring is essential. Etna reminds us that our planet is dynamic and ever-changing. Volcanoes are living systems, shifting and evolving over time. Through science, we turn fear into knowledge, preparing for whatever comes next. By respecting the restless giant, we can live safely in its shadow, marveling at the forces that shape our world.